Hello, my name is Wang. In this video, I'm going to present my analysis of the ABC Bank dataset. The business problem we are focusing on is evaluating the credit card applications. My workflow for this project involved extensive data pre-processing, feature engineering using techniques such as clustering and PCA. And finally, model selection, I use both um, as scikit-learn and H2O AutoML, which means machine learning. The first step is cleaning the data. So the raw dataset requires several cleaning steps before it was ready for modeling. First, I checked if there are any missing values or duplicates in the dataset and using EDA to figure out if there are any obvious relationship between the data. So in my dataset, I first check in the missing values, and the duplicates. Um, then we move to the EDA part, which means we are getting some graphs to figure out are there any inner relationships between these data. Next, I handle the categories of variables. Uh, the machine learning require numerical inputs, so I applied one-hot encoding to features like gender, education level, and marital status. Um, I convert them into binary like 0 and 1 columns. The important step here is handling these um, features because I checked the distribution of numerical features and found that variables like credit limit, average open to buy, and total transaction amount were highly right-skewed. To fix it, I applied a log transformation. This normalizes the distribution and avoids models to learn patterns without being misled by extreme outliers. Back to our notebook. So here I've uh, no. So here I just transparent the uh, many columns into 0 and 1 because the notebook can't analyze the original number. And here I just recheck the screws of the numerical features. Then we move to the feature engineering. The first step is principal components analysis. Um, which means the PCA. The PCA reduces dimensionality by transforming correlated features into a smaller number of components that capture most of the variance. The adventure is noise reduction and potentially better generalizations, but the result will be hard to interpret because principal components are combined of variables and harder to explain. I also use k-means and create clusters labels as an additional feature because applicants may naturally fall into segments, and those segments may carry predictive information. The first model I use is logistic regression. Logistic regression is interpretable and widely accepted in regulated industry. However, logistic regression assumes mostly linear relationships and can struggle when patterns are nonlinear and when classes are imbalanced. The output shows the problem. The logistic regression predicts most entirely the major class, but ignore the minority class. This means that the model is not actually solving the business problem. It can't cover all the classes, although it shows a high accuracy. Next, I will train a random forest classifier. Random forests capture nonlinear relationship and feature interactions automatically, so the output will be improved compared to the linear baselines. Then I use H2O auto machine learning to automatically train and compare multiple advanced models, including gradient boosters and XG booster. The leader board ranked the booster tree models highest by AUC, with AUC value slightly above 0.557. The important technical insight here is that some models show very high accuracy and recall at a fixed threshold, but only moderate AUC. This means that threshold dependent uh, mer- metrics can appear strong while ranking ability remains limited. This reinforces the need to evaluate models across multiple metrics. In conclusion, I would say pre-processing and feature engineering are necessary. Encoding enable model comp- compatibly and scaling enable PCA and stabilize logistic regression. PCA reduces the dimensionality but reduce the interpretability. Random forest feature selection highlighting influential predictors and supported model refinement. Costing adding a segment feature that may capture non-linear structure.